So what you should remember, right, of colligative properties, understanding how to describe chemical potentials, understand dilution effects and what physical processes they cause. And in essence, I've shown you three, right? I've shown you melting point lowering, I've shown you osmotic pressure, and I've shown you a bit earlier concentration effects or electrochemical potential differences. That if I have two solutions with different concentration, I can also get an electrical potential out of that. And in some old exam, I think it's not that old. I think I asked somewhere like how much energy you can get if some freshwater stream, which I think I had some stream in Germany or something, if all the fresh water that comes out of a river, when it mixes with the ocean, if you could actually extract the energy that is getting dissipated there, right? Because the water in the river has much higher chemical potential than the water in the ocean, but it now gets dissipated by irreversible mixing. So it's something you could have a look at. There is also another colligative property, which is boiling point increase, but I'll leave that for you to figure out. So I want to change course a bit and now start making more of a connection with statistical mechanics so that we can understand what the atomic processes are when we mix. Because they will give us more insight in, what is really like ideal solutions, what is Raoultian behavior, where does that actually come from, and when should we expect deviations from that. So in some sense, this is going to lead us to model making, right? Atomic level phenomena in mixing. And they conceptually arise from three parts of the free energy of mixing. If you think of the free energy of mixing at constant temperature and pressure, right? Well, delta G is delta U of mixing, which is an internal energy part, right? Minus T delta S of mixing. Cell phone interruptions, only at home. Plus P delta V of mixing, right? This one we will almost always neglect because this is small, right? Because the delta V in mixing will be small, and even if it were of the order of V, we know that this term is small. So we will deal with this one. This comes from, making different bonds, right? And this comes from making more states when you mix. So where does the delta U come from, right? That if I start with pure A and pure B, here I only have AA bonds and here I only have BB bonds. But when I mix them, I make everything, right? AA, BB, AB. So of course, this is have a different internal energy than the pure states. So I'm going to start with the entropy effect. And so where does that come from? Actually, let me do it over here. Then I have the big board later. So if I do a tiny little system, this is sort of a cartoon system. I'm going to do 2 atoms of A plus 2 atoms of B And they're going to make 4 atoms. In each of these pure states, you know, here omega, the number of sort of lattice configuration is 1, and here omega, let's say omega is 1. But once I mix them, I have a lot of possibilities. If I assume that they randomly mix, so they have no energetic preference, you know, they can take on a bunch of configurations here, right? They can take on this, and I can keep on going. So if I distribute 2 atoms of A and 2 atoms of B, how many configurations are there? Right, it's 4 choose 2. Right, because I have 4 sides, I pick 2 for one of the species, and that means the other ones are decided. So that's 4 factorial divided by 2 factorial divided by 2 factorial, so that's 6. So the reason then a mixture has higher entropy is pretty much this reason, that by mixing A and B, they can now live in each other's phase space, right? When I have a pure state, A has to stick on the A lattice sides, B has to stick on the B lattice sides. When I mix them, they can interchange position, live in each other's phase space, so I have a much higher degeneracy, I have a much larger omega. And if I assume random mixing, that means all these things have the same energy, there's no energetic preference for them, then we can write out exactly what the entropy of mixing is. So that's what I want to do now. So let's solve the general problem. So I want to mix Na atoms, right, which are on some lattice. For now, I'm going to assume that they are on the same lattice, but they don't have to. And so when I mix them, I have a bigger system. And so here I have N, which is Na plus Nb. These all have omega equals 1. But the question is, what is omega here? So if I assume that I can take on any configuration here, then this problem, right? And the underlying assumption of that is, of course, that the energy of all configurations is the same, right? Because if the energy of any distribution of A or B on this lattice is the same, then they can all occur. They're all equally likely. So what is omega here? Well, now it's N choose Na, right? So this is N factorial divided by Na factorial divided by Nb factorial. So the entropy is Kb log omega. So is Kb log N factorial minus log Na factorial minus log Nb factorial. Okay, how do we solve this? Same as always, right? We use Stirling to take the log of the factorials. Out. So this gives us N log N minus N from the first term, and then minus Na log Na plus Na from the second term, and minus Nb log Nb plus Nb. Okay, this N cancels with Na plus Nb, right? Because N is Na plus Nb. I'm going to write N here. I'm going to write this as Na plus Nb. so that I can take factors that I can put NA up front for two of these factors. So what I have is this is NA. I now take this term with this term. So I have NA log. I'm going to keep the minus sign up front actually. NA log NA over N. And I do the same for the B term, which gives me minus NB times log NB over N. NB over N, this is the mole fraction, right? This is XB. NA over N, this is XA. And so if I normalize now by N, so if I write S over NKB, then, then if I do a divide by N here, I get divide by N there. So S over NKB is minus XA log XA minus XB log XB. And so what have I recovered? I have recovered the ideal solution entropy, right? For example, I could set if N is N Avogadro's number, then N times KB is R. So then you can replace this by R, right? And so then you have the entropy per mole. This is a derivation that you should do a few times in your life because it's a sort of classic. It shows up many times in other parts of material science as well when people ask for the entropy of distributions on lattices. For example, it is used exactly the same math is used to show calculate what the equilibrium vacancy concentration is in materials. Right, you calculate sort of the possible distribution of vacancies, and you can show from that vacancies are equilibrium defects, unlike one-dimensional and two-dimensional defects. Okay, so what should you remember here, right? Besides the formula, what you should remember that this is what we obtained when we assumed random mixing. There's no energetic preference for any distribution of A or B on this lattice. We assumed they all had the same probability, right? Because that's why we wrote S is KB log omega, right? And so we literally calculated just how many states are there. We gave them all the same probability, which only happens if they all have the same energy. And then we get the ideal solution of mixing. So let's look at this in the Gibbs entropy context, in the context of Gibbs entropy. Do you think that this entropy is in general larger or smaller than this one? Or is it the same? Gibbs, Boltzmann. Who is the largest here?
Wouldn't Boltzmann be larger?
Yeah. Why?
Okay,
you're allowed to rub your eyes.
From the log omega, you just have. I feel like it's a number of states thing. Like you don't count all of them necessarily with the Boltzmann, but I don't know why that's true to me.
That's okay. You're getting close. I'll help you out. We have talked about this, right? What is the maximum of this distribution? When is entropy maximum? It's when the distribution is flat. The entropy is maximal when pi is a constant, and that means it has to be 1 over omega. Right? Because if there are omega states, the only way that the probability can be a constant and normalized, there's some normalized to 1 is when pi is 1 over omega. So when pi is 1 over omega is when you recover Boltzmann. So this is the maximal entropy of mixing. So anything you do to disturb the probability, right? Anything that constrains the probability will reduce the entropy of mixing, right? So what you need to remember is that ideal solution, which by the way I write as IS because it's too much to write. Ideal solution is the maximal configurational entropy of mixing. That's what this is called, configurational entropy of mixing. Because if I were to plot sort of a probability versus, say, states, so if I have a fully random system, then the probability is flat, right? It's the same for every state. But what if I have energetic preference? You know, maybe A and B don't really want to be totally random on this lattice. Maybe they have preference. Maybe A wants a lot more B next to it, or A wants a lot more A next to it. So then the probability is going to be spread out, right? It's going to be lower in some cases and higher in other cases. So this can still be a solution, but this is a solution with energetic preference. So this one, this here is random. This is sort of more realistic, and this will have lower entropy, right? Yeah, I always forget I shouldn't walk away because then you can't write. Okay.
Then the bound on this would just be when you have like such an energetic preference where you can only access a couple of states, right?
I missed the first thing what you said.
The bound on this would be just like when you have, say, not enough energy to access states, or just a really strong energetic preference for a couple of states. That lower bounds it.
Yeah. Okay. Let me hold your question because I'm just going to tell you how you get lowering of entropy. And if after that it doesn't make any sense, you come back.
Yeah.
Okay, so how can a solution not be random? Right? How not to be random? I feel like this could be a self-help book. I feel like this is not grammatically correct, but hey. Okay, so first of all, you can be non-random even in the disordered state. And that's called short-range order. Or is abbreviated as SRO. So let's say I take a bond. Like I just take like, a nearest neighbor bond. If I want to know the probability that this bond is occupied by both by A. Well, if I'm random, then this is, so in the random case, then these are uncorrelated. So this is the probability that the left one is occupied by A times the probability that the right one is occupied by A. And the probability that each of them is occupied is the concentration, the mole fraction, right? So this is XA squared. Right, because that's what random means, right? like what I put here has no relation to what I put there. There is no energetic preference. So short range order is simply the statement that this is not true, when this is not true. So when PAA is not equal to XA, why am I writing it twice? Then you have what's called short range order. So maybe A prefers to bond with B, and then you will have a strong AB preference, for example, right? If you have like AB bond preference, then PAB will be larger than 2XAXB. Whereas if it's random, then PAB should be 2XAXB. The reason there's a 2, right? Because if you look at an AB bond, there's 2 ways to do that, right? You can do AB and BA. Okay, so this is called short range order. Short range order is real. It's actually present everywhere. Most people just don't pay attention to it because it's harder to measure. It is statistical in nature. It does not break symmetry, so you cannot see it in diffraction easily. It has no symmetry breaking. It's been known since the 1950s and 60s. It was totally forgotten and it's kind of on a resurgence now. People have shown that it affects mechanical behavior of systems, of mixtures. It affects their electronic conductivity. And in our own work, we've shown that it's extremely high for ionic mobility as well. And it makes sense, right? Because short range order tells you kind of what the preferred local environments are. So short range order is very important. And even when you think overall that your solution is a mixture, you still have these short range order preferences. Obviously, the more obvious way when this preference to do a certain thing to make A-B bonds becomes very strong, then of course you can set in what's called long range order. And then you actually do symmetry break. And for example, that's what happens when you do compound formation. So anyway, let me make a simplistic compound here, right? So when they actually start to long range order so that you have translational symmetry breaking, so now you actually have a compound or an ordered state. And if you want to think about how these sort of look like in temperature, if I have a temperature axis, and this is a composition axis, so let's say somewhere a system wants to make a compound. So at low temperature, you would have long range order, or LRO, it's called. There would be a discrete phase transformation to the solid solution state, but the solid solution state would first still display energetic preferences. So you would have a short range ordered solid solution state. And then if you go to really high temperature, right, you would become random. Because at very high temperature, all energetic preferences sort of disappear, right? They play out. Okay, so that gives us some insight into the entropy behavior of mixing. And again, we can sort of only calculate the limiting occurrences here, right? Either you fully mix randomly and then we have ideal solution, or you like have no preference, you only have one state and then you have no entropy of mixing, right? Omega here is 0, or you could say 2, but even 2 disappears when you take the infinite limit. And when you calculate real systems, you're somewhere in between, and so it's a lot harder to do, and you have to do kind of real hardcore statistical mechanics. So what I want to now introduce you is to a sort of somewhat simplistic energy model for mixing. And I'm going to set up a very, very basic energy model. And this is not to imply that this is really how the energy of a system behaves, but it's more to give you insight of what happens upon mixing. because of course the energy of a real system is determined by quantum mechanics, but I'm going to do something very simple. I'm going to write the energy by bond counting. So I'm going to say the internal energy is the number of AA bonds, and I'm doing this again just for binary AB, times the bond energy, and I'll call that AA. So this is the bond energy. Plus the same for B. Plus the same for AB. So I assume I know these three bond energies, AA, BB, and AB, and I can figure out what the energy is. So if I accept that expression, I can calculate the energy of pure states, but actually also of mixed states. So for example, let's do something very simple, pure A, which is not pure A, but pure A. So what's the number of bonds per atom? If I have one atom, right, depends on the coordination number in this lattice. So the number of bonds is the coordination number divided by 2. Because, for example, if I count this bond here, I count it twice because it also is counted from there. So the number of bonds is the number of atoms times Z, which is the coordination number divided by 2. So that means the energy of pure A in this model is Na times Z over 2 times WAA. Okay, so let's now do the slightly more complicated. Let's actually do the mixture, so that then we can actually do the energy of mixing. And then next week we'll discuss about the consequences of that. Okay, so let me make a mixture of A and B now. So I'm going to assume the mixture, I have random mixing, so no energetic preference. So what I need to know is the number of AA bonds, the number of BB bonds, and the number of AB bonds, okay? So if I look at a bond, what's the probability that the bond is AA? Well, if I'm random, that's XA times XA, so that's XA squared. So that means that the number of AA bonds is N times the coordination number over 2 times the probability that the bond is A, which is XA squared. Same for BB, right? The probability that a given bond is BB is XB times XB, which means that the number of BB bonds is NZ over 2 times XB squared. And if I do that for AB, the problem is there are two AB configurations, right? Left and right. So PAB is 2 times XAXB. And by the way, you know that because these have to sum to 1, right? These probabilities have to sum to 1. And if you sum these compositions to 1, you have XA plus XB squared, right? So that means NAB is NZ divided by 2 times 2 times XAXB. I'm going to try to erase here while you can still sort of see that board. Okay, so now let's calculate what the energy of mixing is. So to calculate the energy of mixing, I'm going to have to calculate the energy of the mixture and subtract the pure components. delta U of mixing, I'm going to bring the NZ over 2 up front, is NZ over 2. So I'm first going to write the energy of the mixture. So that's, I'm going to start with the AB bonds, 2 times XA XB times WAB. And then I'm doing the AA and the BB bonds. And I'm going to write the, for AA, the XA squared as 1 minus XB times XA, which is the same as XA squared, right? Times WAA. And then I'm doing the same for B, plus 1 minus XA times XB times WBB. And I have to subtract, this is the energy of the mixture, so now I have to subtract the energy of the pure components. So that's minus Na, which is XA times N, times Z over 2, times WAA. So that's it for A, minus XB times NZ over 2, times WBB. And now there's a few terms here that cancel, right? This term here cancels with this 1 here. And this term cancels with this 1 here. And what I end up with is something that makes sense. I end up with only quadratic terms in XA, XB. So this one survives here. Sorry. This one and this one. And you'll see in a second that makes sense because I can only end up with a quadratic. So if you put it all together, this is XA, XB times N, which is the number of lattice size, times the coordination number. And then some expression in terms of the bond energies. WAB minus WAA plus WBB divided by 2. And this is often rewritten as omega times XA XB, where omega is all this stuff that's kind of constant, NZ. And actually for N is then usually taken N Avogadro, so then this is per mole. So I take N now as N Avogadro times WAB minus the average of the AA and the B bond energy. This is actually in the notes. It's also in the reading by Swalen, which I realize we have to put online. But, you know, again, go through this derivation at one point, but don't lose sight of the trees here, right? Or the forest, confused. In the end, what do we find? What we find is that in this simple model, the energy of mixing is a quadratic in the composition. And it has to be, right? Because a quadratic is the simplest function that is 0 at pure A and at pure B. Because the energy of mixing has to be 0 at the end members because I'm not mixing anything. So I can't keep any linear terms. So it is the simplest function. It's a quadratic in XA and XB. And the prefactor, right, the energetic quantity, what does it contain? Well, it contains some like stupid reference stuff, right? The fact that we're doing it per mole, so N is N Avogadro. Z is just a small integer, right? It's the coordination number. But the important thing is this here, right? Omega is proportional to the bond energetics. It's essentially proportional to the new bonds you make in a mixture, which is the AB bonds, minus the average of the AA and the BB. So the energy of mixing seems to be proportional to the difference between the new bonds and the average of the old bond energies. That's how you could think of it, right? So that's how you sort of conceptually should try to remember this. So very often, people will call this the enthalpy of mixing and not the energy of mixing. Technically, it is just the energy of mixing, but since the P dV delta V term is very small, they are kind of the same, right? And so that leads us to the definition of what's called a regular solution. And again, you know, this is an old thermodynamics name from old metallurgy, and there's nothing regular about a regular solution, but it's the name, which a regular solution is one where the free energy of mixing is the quadratic for the enthalpy, XA, XB, plus ideal solution. Right? So this here is ideal solution. So I'm going to leave you with a thought that there's something pathological. I think in science, people like to use the word pathological, which of course is from Greek, right? Pathos, which kills you. There is something pathological about a regular solution. There is something sort of fundamentally inconsistent between this term and that term. And you should think a bit about that, right? I'm going to tell you, it still works, but there are limitations to it, and it will work better at some temperatures or at some conditions than others because of this pathology. So give that some thought, right? Like, what are the conditions under which we derive this? And what are the conditions under which we derive this? They are not completely consistent. So give that some thought. And what I will do is in the next lecture, I will pick that up. And I realize because I'm canceling Monday, I'm taking a break. So